Good afternoon, everyone. My name is Changjie from Wenzhou Kean University, Wenzhou, China. It's a great honor for me to present my paper here at the CVPR Precognition workshop. Our team contains 3 members, including my senior Shen and my professor Gaurav Gupta. My title is Unsupervised Domain Adaptation for Cardiac Segmentation towards Structural Mutual Information Maximization. Here are 4 types of cardiac images, including CT, MRI, PET, and US. They have different statistical distribution. However, each modality plays a complementary role in cardiac disease diagnosis, and the manual annotation consumes 2 to 4 hours. How can we annotate one modality without label, transferring knowledge from another domain? That is how to deal with domain shift problem. Here are 2 common strategies. The first one is gun-based. They use a cycle gun to transfer the style from source to the target. Then the classifier will play the adversarial game with a short encoder to minimize the domain discrepancy in the feature space. Another method is VAE. They will minimize the domain discrepancy in the latent space explicitly, because the latent space is normal distribution. We still found that the second method has a large space to step forward. We deduce a compact loss lower bound, discovering a new mutual information term. We design a normal plug-and-play style structural mutual information estimation block. To minimize the invariant, we convert the parallel reparameterization to sequential reparameterization. Here are some samples and description. Our model is to maximize the joint log likelihood of the complete data, where the X is the image input, Y is segmentation output. We deduce a lower bound to estimate the log likelihood term in the equation 3. Here are the breakthroughs. We use the variational method and the base rules to get the terms in equation 4. Note that the UDA-VAE neglects the term of KO divergence as it is greater than 0. In comparison, we deduce a compact lower bound with the following term in equation 5. Consider the reconstruction area of the VAE. In equation 6, we can replace the KO divergence of the joint distribution in the equation 5, so that we can get term in the equation 7. Finally, we deduce the compact lower bound in equation 8. Since the R log term and the entropy term are constant, we have to maximize the mutual information of the X, Y, and Z, where Z is a latent variable. Here is our methodology. Our architecture contains a UNet with 3 scales of variational blocks. To maximize the mutual information of the reconstruction output and the segmentation output, we design 3 mutual information estimation blocks in gray. Estimate the mutual information is very difficult. The mutual information is defined as a KO divergence of 2 variables, joint distribution and marginal distribution. The Donsker in 1975 proposed a dual representation, which contains the T. For easily understanding, the T is a set of all possible neural networks. This method can estimate the mutual information using the gradient descent method. And another one is deep informatics. However, we are interested in maximizing the mutual information rather than obtaining the exact value. So we can use the contrastive learning in the equation 11, where Y hat and R are the segmentation output and reconstruction output, where R apostrophe is random sampled from the reconstruction output. So we want to maximize the positive pairs the mutual information, minimize the negative pairs mutual information. Here are 3 blocks, including the global mutual information estimation block, local MI block, and the probability information matching. And the loss function, as I introduced before, the first one is reconstruction loss. It contains 1 KO divergence in the latent space and the reconstruction output. And segmentation is coarse entropy. And domain discrepancy loss we can minimize explicitly since they are all normal distribution. And the structural mutual information block contains three terms, the global, local, and provincial. And total loss is formulated in equation 20. We use two datasets. In each experiment, we will delete the one labeled from one domain. Sample contains about 40 to 80 slides. Here are the results. The left one is the MRI images. This one is one truth. This one is CFD-net. This one is UDA-VAE, and this one is our method. This is a reconstruction images from MSCMSEC dataset. You can clearly see our method have very clear structure output compared with the original UDA-VAE method. We use dice and the average symmetric surface distance matrix to estimate three components of cardiac. This one is from MRI to CT, from CT to MRI, and another dataset. You can clearly see that our method achieves the state-of-the-art performance. We also do the ablation study. SR means a sequential reparameterization. This is attention, global mutual information estimation, local one, and the parallel information matching. Each component increase overall performance. Here's our conclusion. This paper introduced UDA-VAE++, an unsupervised domain adaptation framework for cardiac segmentation. We deduce a compact loss lower bound and design a MIME block to evaluate it. We introduce a sequential reparameterization design allowing information flow between multi-scale latent space features. Our model achieves state-of-the-art performance on benchmark datasets. For future work, we will want to extend to other medical image segmentation tasks, for example, the brain image segmentation. Thank you for your listening.